Welcome back. Uh, this is going to be the second part of our discussion of the trapezoid rule. And again, we're going to be going through the Mathematica notebook, trapezoid rule new, that's posted on the web page. So you can play along with this yourselves as you watch or just look at it later. So we saw in the handwritten notes that the error bound for the trapezoid rule looks like this. Uh, that is the difference between the trapezoid rule with n intervals and the actual value of the integral is less than or equal to 1/12 times m times the length of the interval cubed over the number of subdivisions squared. Now it's important to know that this is a hard theoretical bound, so this is always true. This is not approximate. Um, and for that reason, it can be loose. The error is always guaranteed to be less than this, and it can be much less than this in certain circumstances. The other thing to notice is that this requires an overestimate m for the absolute value of the second derivative on the interval. Okay, so the first use case for this is somebody says to you, um, we need this integral and we need it within an absolute error. Notice this is an absolute error bound of 0.01 or something. So please solve for the number of subdivisions required and code that. So you can solve this equation by hand, of course, but since we're practicing using Mathematica, let's just do the algebra automatically. So here we go. And you'll notice that this is kind of weird. For instance, it has an I in it. Um, there's one solution that might be negative, one solution that might be positive. And the problem is that Mathematica doesn't know that b is supposed to be greater than a, so it's worried about taking the square root when you solve for n. So you can make it look a little bit better uh, by replacing this with the absolute value of b minus a cubed over n squared, um, which at least makes it clear which solution is the positive one, that's this one on the right, or which solution is the negative one, that's this one on the left. I actually played with this for a surprisingly long period of time, adding assumptions and taking them out and messing around with it to see if I could get Mathematica to come up with something better. But really, this is about the best you can do. So the last point to remember is this is, of course, some weird real number, and n, the number of subdivisions, has to be an integer. So you have to round up, which you do in Mathematica with the ceiling call. So here's what it looks like as a function. I just copied this and pasted it into here. I'll do that again so you can see it. Um, Copy, Command C, paste, Command V, and notice that it preserves the formatting, which is kind of what you want. The general principle in Mathematica programming is make the code look as much like the math as possible, because that reduces the chance that you'll introduce an error. So I get the required trapezoid intervals, and I'm just composing the result with n. This at is the same thing as writing n brackets of that, but it looks nicer. So you can read the at sign as of, so this reads n of ceiling of this stuff. Okay, so I'll evaluate, and now for our test integration, the integral from 0 to pi over 2 of sine, you know that the second derivative of sine is minus sine. And we're evaluating over the interval 0 to pi over 2, where minus sign goes from 0 to negative 1. So m equals 1 is the smallest bound on the absolute value of this second derivative that will work. So supposing we'd like to get this integral accurate to within uh, 0.001. We can compute the number of required intervals and see that the theory predicts that 18 intervals are guaranteed to suffice. So let's actually do it. Uh, we're going to measure the error with 18 intervals, and we see that it is indeed less than 001, 0.001. So here's an example, by the way, of using the integral sign from the Math Assistant palette in code, and it works just fine if you paste this thing in. Uh, if you do it piece by piece, it seems to be a little more flaky. But if you, I'll show you how I got this by deleting it and clicking over here. Okay, so the blue box is down at the lower limit, so the lower limit is 0. Tab, the upper limit is escape p escape, that's pi over 2. Tab, the integrand is sine of x. Tab, the variable is x. And then I hit Shift Enter and it computes it. Okay, now the other use case for the theoretical error bound is when you take the number of intervals to be known and ask how good the approximation to the integral is. And of course for this, you're just plugging in the formula we derived in the notes. So I'll predict the error for 18 intervals. Notice that the error bound is a little less than 0.001 because really, 17 point something intervals would have hit it on the nose, but 17 point something intervals is impossible.